Alright, so we're going to talk a bit about question number 6 in the lecture activity. And specifically, it's this bottom part of the question because I actually answered how to figure these out in the main video where I did in lecture. So, what intermolecular forces exist within each of the three compounds, and how do these forces affect the melting and boiling points? And so the first step you have to understand, I went ahead and played this video so I can show you. This thing makes it very easy for you, and you can cut out quite a bit of the work you normally have to do. But the first step to always understanding these sort of problems and being able to apply is to understand the concept itself. So intramolecular forces are the forces between molecules, right? And so two water molecules are going to have certain forces that cause them to be attracted to each other. And those forces are going to be what hold the molecules together into a solid, and breaking those forces is going to be what makes it into a liquid then, 20%-ish being broken, and then breaking all of them is going to turn that into a gas because they won't be held together anymore. And so the first one you have to understand is the London dispersion forces. London dispersion forces are everywhere all the time, okay? So London dispersion forces are all of these. All of these have London dispersion forces, all right? Every single molecule will have London dispersion forces with any other molecule. It's just how strong are they? And so, for example, in water, they're not particularly strong, and then you have much stronger forces holding those together. And so the London dispersion forces, while there, are just not that significant. Something much larger, like benzene, is going to have much larger London dispersion forces. And London dispersion forces happen because there's uneven distributions of electrons around molecules. So, yeah, most of the time the electron density is going to be relatively even around it, but just like the lecture hall, every now and then you're going to notice where one side of the room fills up a bit more than the other, right? And it becomes kind of obvious. Well, when that happens to charged particles, that's going to create a temporary negative charge and a temporary positive charge. And those are going to be attracted to any temporary negative and positive charges nearby. And so that will create a very temporary attraction, which is fairly weak. Unless you have many halls, right? So if you were to look into hundreds of lecture halls, you almost certainly would find one that's uneven, right? Or probably a lot that are uneven. And so if you have very large molecules, very large atoms, then you start seeing more and more London dispersion forces. And so, for example, London dispersion forces are going to be very large in benzene. And I'll show you what it looks like in just a bit, but first I wanted to explain the forces. So the next force you should concentrate on, think about, is the next weakest, which is dipole-dipole. Dipole means two poles, and so these are going to be two magnets. You have molecules that have a positive and negative end to them. And when these get near to each other, the positive end of one is going to be attracted to the negative of the other. Just like magnets, hopefully you are getting that part because that's... if you aren't getting that part, you really just need to come by my office and play with the magnets I have in my office. Because frankly speaking, that's it. It's all you really need to know about that. The only part that you may be forgetting is a review of Lewis structures. If you don't remember how to write out your structures of molecules and figure out if they have dipoles, then please ask me specifically that. I actually have a series of videos already up that will teach you from the ground floor up on how to write out a Lewis structure and then identify its dipoles. So anyways, dipole-dipole interactions are just the molecules have a positive and negative end. You know that they'll have a positive or negative end if they have electronegative things on one end and things that are not very electronegative on the other. And remember, electronegativity is how well it holds onto its electrons in a bond. And it's the highest at fluorine, and it goes down as you go left and down. So the next force that we need to talk about is hydrogen bonding. And remember, that's a very special case of dipole-dipole interactions. And again, this is something I actually already recorded in the lecture videos, but I'm recapping it here because if you just look at this, it won't make any sense without it. But please, again, you absolutely need to get your terminologies and concepts down. Everything else builds off of them. You will not be able to do anything else if you don't understand basic concepts like this. So please make sure you get them down. Please, if you aren't understanding, ask me to describe it in different ways. Be very specific that I'm not understanding how dipole-dipole interactions work, that sort of thing, okay? Okay, so hydrogen bonding happens when you have hydrogen, oxygen, nitrogen, or fluorine. So a hydrogen bonded to an oxygen is going to give you something that can hydrogen bond with something else. And so a acceptor and donator is needed for hydrogen bonding. For hydrogen bonding to happen, you have to have an exposed electronegative atom like oxygen, nitrogen, or fluorine, and you have to have an exposed hydrogen that is bonded to an oxygen, nitrogen, or fluorine. So water is the simplest example of hydrogen bonding, and if you go ahead and look at this, so you see these magnifying glasses, hit those, and it'll show you the molecules and sort of what's going on in there. And so if you go to crystal, this right here is the solid crystal, you'll notice these are all lined up very nicely. The red, which is oxygen, and then the whites, which are hydrogen. And so the white hydrogen, which is positively charged in water, is aligned with a red negatively charged oxygen. And that is happening in repeated patterns. Notice the hexagonal shape. That's what makes things like snowflakes and that shapes of water crystals. Then you break a significant number of these bonds and you get something that looks more like this. This is a really old model of water. Anyways, the actual molecular shapes of water has these little cluster shapes. It would have been more correct to like cut out a little portion of this and then just have parts of it that are flopping around, not the whole thing jiggling everywhere like that. That's not actually what water looks like as a liquid. Anyways, it gives you a fairly decent understanding. See that still the negatively charged ends are associated with these positively charged ends. If you look closely, you'll see that this is always pointing towards one of these oxygens. And that's fair enough. These do break and reshift and reform quite often in the liquid form of water. However, overall, you're still going to have that hydrogen bonding, which will be the positive hydrogen attached to a negative, in this case, oxygen. And remember, you can always tell hydrogen bonding because you're going to have an oxygen with a hydrogen, a nitrogen with a hydrogen, or a fluorine with a hydrogen bonded to it. Okay? That is hydrogen bonding. You can't get it anywhere else. Okay, so the next one is going to actually be ion-dipole interactions. And it would be, again, one of the molecules has a dipole, and it would be attracted to an ion. So remember, ions come in cations, positive, anions, which are negative. And so if you have a cation, it would be attracted to, let's say, the negatively charged oxygen in these water molecules. And those would make little shells around it, right? In this case, you don't have any ion-dipole interactions you really need to worry about. We've skipped that. And so we look at water here. You can see this is the gas, by the way, where you've broken all of the intermolecular interactions. Anyways, so that's water right there. And see, it shows you the molecule of water. So we look at the molecules of water. Again, it has a positive end, it has a negative end. The positive end's the side with the hydrogens. The negative end's the side with the oxygen. And specifically, it has oxygen bonded to a hydrogen. And so your water molecules have to have hydrogen bonding. And they also always have to have London dispersion forces, okay? They always do. That's just if you have a molecule, if you have an atom, it will have some degree of London dispersion forces. They could be fairly weak, but still, they'll be there. Okay, so the next one we'll look at is bromine. That'll be the next one. I need to play it real quick. It goes pretty quickly, luckily, because bromine evaporates very fast. And then if you actually click on these, you'll see what bromine looks like as a molecule. They made it brown for some reason. Typically, they represent it by like a deep wine red. And that's actually because bromine looks like a deep wine red in most solutions. But I kind of get where they're getting brown from. They're doing the non-solution bromine, which sometimes looks a bit like a brown gas. Anyways, they look like chocolate. I guess I'm hungry. Anyways, again, if you look very closely, there are two BRs. They are bonded together with a covalent bond. They do not have any pull because they are the exact same atom. It would be like two people that can pull the exact same amount of weight. They're going to balance, right? If you put them on balance. And so, bromine bonded to a bromine is going to have the exact same electronegativities. It'll have the exact same amount of electrons around both. It'll be neutral overall completely. It has no ability to do any of the other intermolecular interactions that I've talked about. The only interaction it can fulfill is the one that is there for everything, which is London dispersion forces, right? And so that is the only one bromine can do. It doesn't have any other options. It doesn't have any difference in electronegativities. It doesn't have any difference in the sides. It doesn't have any differences. It's the same atom twice. Same element twice. And here's benzene. It's going to take a little bit longer. Alright. And so we're melting. By the way, that's how you tell the melting point. You would trace them over. If you want it to be much easier, you'd click on text-only version, which would give you the numbers, and you'd go to the ones that repeat over and over. And those would be your melting, then boiling points, obviously. Okay. Now we're going to open this puppy up so we can see what the heck these look like. And that's actually somewhat difficult to see. If you look closely at the liquid one, which isn't moving so fast, you can see that it's 6 carbons if you count closely on one of the flat ones. See, like that one and that one, or they're all flat. If you count the number of black things in the middle that are sort of vibrating around, those are carbons. And so it is carbon ring with 6 carbons in it. And then it has 1 hydrogen off of each carbon. Now, at the beginning of General Chemistry 1, you should have been taught how many of each, well, by the end, definitely you should have this, but at the beginning you should have been taught basic organic molecules, how to write them, how to read them, how to read a line angle structure. If you guys weren't taught that for whatever reason, please let me know. Or if you just don't have the ability to access that in your notes and can't go back and look at that, because I can reteach that. It's not that hard, but I'll have to have its own video and stuff. And it's something that you should have covered like chapter 8, 9. Yeah. Anyways, and you should have actually covered it in chapter 2 as well. Anyways. So carbon in benzene has a series of double bonds in it, but overall you don't need to know that. It's actually a very interesting structure if you want to ask me about that sometime. But overall you can look at these and see that they are entirely symmetric. See that? They don't have different ends. They just have the same in every direction. And so if they're symmetric, they definitely don't have dipoles, do they? If they don't have dipoles, they can't be anything else but London dispersion forces. Because all the rest of those things, dipole-dipole interactions, hydrogen bonding, dipole ion, those all involve a dipole in some way. Hydrogen bonding is just a very special dipole-dipole interaction. So again, those all involve dipoles. They have to be non-symmetric structures, anti-symmetric or asymmetric structures. They could never be something symmetric like this. And on top of that, hydrogen and carbon don't actually have enough difference in electronegativities that they would be normally considered polar. Okay? And so these are, again, non-polar. They do not have poles. They do not have dipoles. They are only London dispersion forces because that's literally the only thing you can do with them. They simply do not fulfill any of the requirements to have any other force. Hopefully this makes a bit of sense. Let me know if you still have questions about this, if you don't understand something about this. It helps if you give me more specific questions because, again, the more broad your question is, the more broad my answer has to be, right? And I just simply cannot go through from Gen Chem 1 all the way through here to make sure that you picked everything up before. There's not time for it. I did post videos on it though, so I guess technically I did that, but you probably don't have time to watch through all those either. So the more specific the questions are, the better. This was a very good question, by the way. Don't think I'm talking about this. I just am trying to get you guys warmed up into what's going on here and, get some dialogue there. You guys take care. Let me know if you have any issues, if you have any more questions, whatever. Again, we're all adults. We can discuss things and come up with solutions. You take care now.